Ever heard of the nitrogen crisis? It's a problem we caused ourselves. Since the Industrial Revolution, humans produce vast amounts of artificial fertilizer using fossil fuels. Reactive nitrogen in the form of ammonia is one of the main ingredients of these fertilizers. With production quantities ever increasing since its discovery in 1909, synthesis of ammonia-based fertilizers make up for almost 2% of the global energy consumption, contributing substantially to global warming. Additionally, excess ammonia ends up in natural ecosystems, posing a serious threat on biodiversity worldwide. So how does this work? Nitrogen exists in various forms. 78% of the air is inert nitrogen gas. The reactive forms, ammonia, nitrite and nitrate, are compounds used by plants for growth. The conversion of inert nitrogen to reactive forms is carried out by bacteria living in the roots of some plants. The plants, in their turn, use sunlight to create sugars for the bacteria. This tit-for-tat comes at a price, though. These sugars can't be used for plant growth. When sufficient reactive nitrogen is provided to the plant by other means, the plant stops the sugar supply and grows faster. This principle has been used for ages. In pre-industrial agriculture, humans used manure and compost, both rich in reactive nitrogen, to obtain faster plant growth. After discovering how to make reactive nitrogen using fossil fuels, we really put agriculture on steroids. And just as with steroids, this short-term fix comes at a long-term price. Often these reactive forms of nitrogen are administered more than what the naturally occurring soil bacteria could supply. Large amounts are not even taken up by the crops and leach out into the surrounding areas. Another part of the nitrogen ends up in the crops as intended, but after these crops get eaten, it ends up in wastewater and manure through the excrements of humans and other animals. Manure processing and wastewater treatment aim to degrade this nitrogen waste as much as possible. However, these processes are energy-intensive. In addition, part of the reactive nitrogen ends up in natural environments, causing serious damage to biodiversity. So how do we fix the old fix? Can't we go back to the old ways, letting the soil bacteria do their job, applying some compost and manure here and there? Sure, but that way it won't be easy to feed the current human population. The N.E.W.B.I.E.S project might provide us with the solution. By selectively recovering ammonia from wastewater, N.E.W.B.I.E.S allows reactive nitrogen to be reused as fertilizer. It achieves this through a two-step process. Using electrodialysis, ammonium is extracted from the wastewater into an alkaline concentrated stream. Subsequently, the ammonium becomes gaseous and is transported over a gas-permeable membrane. It is reabsorbed into a slightly acidic solution. Depending on the composition of the wastewater, the resulting fertilizer consists mainly of aqueous ammonium, nitrate, sulfate, phosphate and chloride, providing a balanced fertilizer for crop growth. Energy used this way is as low as 10 kilowatts per kilogram of reactive nitrogen recovered. Moreover, N.E.W.B.I.E.S reduces reactive nitrogen leaching to the environment, minimizing further damage to the ecosystem. N.E.W.B.I.E.S is made possible by W&F Technologies, ICRA, the Catalan Institute for Water Research, N.E.W.B.I.E.S, WWTP, and founding program EU Life.